will work, but we're doing our best. All right, so that's watching me, watching you. I think I can get rid of this. No, that's not quite right, is it?
You have ads running on your channel?
No? Which channel has ads?
The Twitch.
Oh, we'll turn those off then. They're not sending me any money.
Oh, maybe that's right.
Twitch.tv/McQuarrie.
Oh, it's just because it's like a dodgy ass non-whatever account. This doesn't seem to be streaming, so I'm just trying to keep an eye on that.
Yeah, I can hear you pretty well.
What's the Twitch link?
But what's on the picture? The picture seems to be something funny.
It's just I'm looking. Yeah, it's working well now.
But the picture, is it updating?
Not yet.
No.
Well, it's just on the Island page.
Yeah, but I'm changing the island page.
No, not yet.
Something weird's happening.
It'll be
Your game and title again.
It sounds working nicely.
Yep, good. Well, let's try and get the screen working as well. I think it's because the what's the word I'm looking for? The resolution got changed and it's probably having a spaz out. Yeah, remove that. Stream nothing. Add it again.
Right now.
Yep, and it should come back in a sec.
Oh, yep.
Good to go. All right, it was the resolution change from plugging in the external monitor. You learn, live and learn. Okay.
That's good.
Sounds fine.
All right, well, we'll do that one not first. I'll start up. I'll let Irene ease into it. But Cognition of Coding is Irene's project. I didn't grab those slides yet, so
Yeah, I have them.
cool. But it's easier just to have them on here. But we don't need to stream yours as well if you don't want.
It can if you want it
Cool.
to be.
Yeah, it's easier just to do it all. So let us start with... Now, some of you are already working on some of these, so you've got an idea what you already want to work on. Some of you have no idea what the heck I'm about to talk about. So, with this one, I'll be going into quite a bit of detail because there's quite a lot going on. Just let it wash over you if you don't really understand. Oh, so I should explain the purpose to those who have not been here before. The purpose of this is just to get you something interesting to do for a week and exposure to what research means at a university. Because that's actually, there's a lot of misconceptions about how it goes. So we just do research for a week at the level that you guys can contribute, and that's it. So you contribute what you can, you don't stress about what you can't, I've done this a few times now, and we always get useful stuff out of the process, so you don't have to worry about whether you actually are. A lot of people feel like they're not contributing, but don't worry, you are. One of the valuable things in research is having multiple points of view, and one of the things that doesn't happen often enough. So even just being there, giving a point of view is a useful thing. Half understanding the problem. The other thing about research is that you never really understand what you're doing. And if you did, it wouldn't be research. So you've got to be prepared to only half understand and still push on. And that's something that's not natural, particularly to students who've done well most of the time in their study. They generally know what's going on. They generally have the answer to any question you ask them, but once you're doing research, you don't have the answer to any of the questions. Took me a while to get used to that, but I'm very used to it now. I just spend my time permanently confused, as you've probably noticed, and I just go with it. Okay. So, skin response data. This one's been going for, is it 18? No, 1 year. We started this 1 year ago. Yeah. We've had a few people heavily involved in it, but they can't come in this year. But they'll be tuning in to the recording probably to see exactly where we're up to. And then in the meantime, since the summer project where we did a lot of work on it, I've been working very hard on this with Carly. And so it's gotten to quite a sophisticated state. Still tons of work to do. We now got some discussions with the company that runs the software you're about to see. So that's another reason to be recording this. I think they want to see what we've been doing. So that way I'll have a recording of what I've been doing. So some of the stuff I say might be directed more at them than you. Just go with the flow. I need to get a remote desktop up. And not that lab chart, the other lab chart. So this project runs on special software that has expensive license that we don't have multiple licenses for. So we have a machine set up specifically with access to that. that I'm just about to log into, if I can find the right IP address, so I can show you it in action. Yeah, I guess it's a new desktop, and it's 10.6.29.98, and I'm working on trying to get you guys access to these computers so that we can work in here, but if we can't, then we'll end up going downstairs after lunch. But you don't need access to the computers to hear me prattle on, I suppose. Friendly name is GSR, and we'll add. So fingers crossed I can log into this so I can show you. Yeah, that's fine. Oop, that's something else you don't need to worry about. That's something else you don't need to worry about. That's something else you don't need to worry about. No, that's alright. And another one. That was the weekend's work. Save that. Oh, jeez. I don't know. Temp? No, not temp. Just there. Okay, here we go. All right, the software in question is this thing called LabChart. So 2 years ago, we collected some data with this machinery and started analyzing it. And since then, the Center for Emotional Health has collected hundreds and hundreds of data sets, participants' data that needs analyzing. So this is an example of one of them. It's what we see here on the red curve is the conductance response on somebody's fingers during an experiment, and what we see on the blue curve is their breathing during the experiment. The little bumps in the breathing here probably are just them moving or something. They didn't really take a giant breath at that point. But the peaks and troughs in this one should be corresponding to stress. And so the experiment runs and it does various things to the people, shows them things and plays noises at them, and they get stressed or not stressed over the length of the experiment. So in general, we see these curves rising up because things are happening. The green curve down here is the... oh no, this is just me experimenting. That green curve is nothing at the moment. But you can add multiple channels into this system. So this was an experiment to try and get a smoothed version of the top one, but it didn't really work out. What we do with that third channel during the experiment is set it up to be the derivative of the first channel. So is this the one I want? No, that's not the one I want. I've lost track of exactly which one I use. Derivative, of course. And I need a big window and okay, whatever, it'll do its thing. And that's just not very good at all. So getting the derivative data is a bit finicky. We've got it all coded, so don't worry too much about that. But you will need to know that there's multiple channels going on. There's 2 recorded channels and then other channels that we generate. All right, so there's an algorithm for this, for working out when someone's gotten stressed and when they haven't. The way it works is that the data is full of these little markers we can see down the bottom. Here's one that says CS plus on, and then there's an ITI on after it. So this period here that were marked out by the markers is a period where something might have happened during the experiment. And then the periods in between is when nothing really happened. So something might have happened here, and the job of the analysis is to work out, did the person get stressed during this period? And you can tell if they got stressed by looking for rises in the data. So there's all kinds of rules about how we should capture this data. The rules are...
That's what the stream shows, just for reference.
Cool. Not quite the whole page. Thank you. Just keep it in the top left. There's all kinds of rules for how to analyze this data. For example, in this particular section, which we call an interval, I would like to count from here to here, which is a rise. Now, I'm not counting this second rise over here, even though it goes higher, because that's one of the rules. Just count the first one. I'm not counting this first rise here because it starts before the marker. That's another one of the rules. And we got an algorithm, we got a program that goes through all these files and just takes all the intervals, bam, 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 runs the algorithm to decide what the response is, bam, 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 and then spits it out in a big file. But it's quite complicated. So that's the job it's doing. Each file is made up of phases. There's 4 phases in each file. I can't show them to you because it's hard to find the markers for them. But for example, there might be a phase that runs from here to here that's got 4 of those intervals inside it. There might be another phase running from here to here with 8 of those intervals inside it. And then maybe this is another phase with another 4 intervals inside it. So to analyze this, we've created Ruby code. So we started off with all kinds of other things. The system has a built-in macro system. G'day. The system has a built-in macro system, which I just ran the macro, I didn't want to run it, I wanted to look at it, where you can program automated analysis, and it looks like this. And that was what we did a year ago, and then 6 months ago we took it out of the internal system and moved it to an external system because we hit the limit of what was available on the internal system, and turned it into some Ruby code, and now the Ruby code has grown. So this project, which is barely visible on that screen, is a Ruby project for doing that analysis. It's got lots of different files in it. I'll just give you a quick rundown of what the files do. There's a VS Code section, which is just for the editor here. Don't worry about that. There's also a web page that goes with this, and that's kept in here as well. So that's what the CSS and the JS and the index.html and the curvebuilder.html are. So they're to do with the website. I think I linked to that from the iLearn. And then there's a Bitbucket Pipelines is for automatically running the, what do we call it? Well, it's the continual build, but I use it for publishing the website. And then there's all the Ruby files that do the actual analysis. There's one other file that doesn't do analysis, which is, not here. I didn't include it. Okay. I'll have to add that from the other one. We've also got a, what's it called? Jupyter Notebook for doing the analysis. But all these other files, block local time RB, document RB, GSR analysis RB, interval RB, logger RB, main RB, all these are the Ruby files for doing the analysis. So there's a lot going on. And at the moment, it's been built over a year, and we've lost track a bit of all the complexity in there. We know that it's working, we know that it does what it wants, and we know we can describe the main part of it, but there's a heck of a lot going on in that code. So I understand it, and a few other people kind of understand it, but we need to get to the point where we've got written explanations of what that code does and a better understanding of it. The main file that runs it is this guy run.rb, and that'll run the full analysis with however many files I ask it to. But there's also a test file, which is the most useful one for us this week. This test file has known answers to all of the questions that we might ask. And so, for example, it looks a bit like gobbledygook, but for example, this one's saying that if I go into the return phase and look at the CS plus interval and check out the second part of that interval, I'll find out that the person had a 0.06 response, and so on and so forth. The reason this is cool is that we can rerun this test over and over again to check that when we make changes to the code, we keep getting the results we expected. This is our regression testing. So what we're likely to do this week is to build out some more of this regression testing, which involves looking at the files ourselves and deciding whether there's a response there or not, and then encoding it into the test file to see if there is a response. And we'll do that on some of the harder programs. You see, I've got lots of little to-dos in here for things where I've got questions about whether the answer is the right one. That's okay. Okay, so the main job here is, well, understanding this Ruby code. It's a bit of a code dive for what I think is overall a really interesting project. And once you've done that dive and understood some of the code, you'll be able to help us write that code. You'll be able to help us to write the papers that are going to go along with this code, and help us work with the company, hopefully, who want to know how we did this and want to incorporate some of these ideas into their own product. way more detail I could go into there, but I just don't. I think I'll save that for later. There really is just too much to talk about on this one. For example, this log shows you all the things the algorithm's done, and you get thousands of lines. So this looks a bit overwhelming, but if we take it little by little, you can get into the code and understand what's going on. And don't worry whether you know Ruby or not. Ruby's fairly easy to pick up from any other programming language. You might have to do a bit of reading on Ruby syntax and things like that, like what does the at mean and what's an initialize function, but I don't think it's too bad. Are there any questions on this one? Any things I can clarify that I didn't discuss yet? No? Okay. All right, so that's the GSR one. And as I said on the... So you guys can get logins to this machine, and one or two of you already have logins. And so a lot of the work will be done by logging into that machine if we can get you access to these ones, and working directly on that machine, looking at the data. Because we can't take the data elsewhere. We can't install the software elsewhere. It's stuck there. So we have a web... Is this coming up to the right thing? Yes. So this is the website that's included in that repository. When it gets published, it looks like this. It's got descriptions of what the algorithm's doing, and we want to expand this out. So it's only got descriptions of what it's doing in obvious cases. There are lots of other cases you might think of, and we can't think of them all. So it's good to have extra minds thinking, well, what could this curve look like, and what would it mean if the curve went from this to this? Should I count a response or should I not count a response? And we'll know the answers to those, but we won't have written them down and we won't have codified them in the algorithm. So that would be part of what we want to do. And the other thing is, at the moment we're writing the paper describing the algorithm. So we'll probably have some of you working on this as well, helping us to write this paper. But to write the paper, of course, you've got to understand the algorithm. So there'll be some work there beforehand. So this is a paper we hope to publish this year, describing the algorithm. It's a more academic version of the website. The website is for a general audience to describe what we're talking about and what we're doing, and then there's a paper that hopefully we can get published for academic audiences describing exactly what's going on so other people can replicate the experiment if they want to, which they should. Okay. Just trying to get that window down to the size of the stream. I can see it up there. Hello. Cool. All right, there we go. That means I can put hidden things down below. Go away, mail. How below we all gonna go? Okay, so that's the GSR project. So I'm going to spend, notice up here, sorry, I put a kind of main focus thing. In previous years, I've gotten a bit overwhelmed trying to keep on top of everything. So my plan this semester, or this winter, is to visit each project after lunch and in the morning to see where they're at and just talk to them about where they might go. But then to sit down with each project for the whole period and concentrate on it with them. But to do one project at a time. So my plan for this afternoon is to sit with the GSR people who've chosen that project and to get right into it, and then tomorrow morning to sit with the Wali people, tomorrow afternoon the patterns. But again, at each break, when I come back from a break, I'll run around and have a chat and see where you're at and point you so no one's getting stuck. That's the plan. And then I did one for Irene too. It's just going to be working on the cognition of coding all week. Thank goodness. All right, the Wali project. So Wali is an extended static type checking language, which only a few of you have had some exposure to. Joseph has. Elise has. And the aim for this project, so extended static type checking is a thing on its own. I'll give you an example of extended static type checking. It really is not very big, is it? Come forward if you can't. Do I need to make it bigger so people can actually see?
Open the stream.
Hmm?
Like their phones. We're watching the stream.
Oh, cool. Well, as long as you can see.
Yeah.
That says something about the world, doesn't it? Just trying to find an example of Wiley code so I can show you.
If you go to the web ID, it just has some video.
Yeah, the web ID's been a little broken recently, so I wanted to. Alright, so yeah, I can make things bigger. So this is an example of a function in Wiley, and these two lines here are the things Wiley does that other languages don't do. You can put in things that are guaranteed to be true of the code, and Wiley would check them to make sure they're true. So this one says if I've got a function called absolute, or abs, and it takes in one integer and gives back another integer, then I guarantee you the integer that comes back is bigger than or equal to 0. And I guarantee you the integer comes back is either equal to the one you gave me, or it's equal to negative times the one you gave me. That's exactly what you want an absolute value function to do. This is completely obvious in this example. There's no trick here, right? But you can expand this further and further and further and write more and more complicated functions and still have guarantees of what they do. So here's an example function, index of, which takes in an array of items and then a particular item in that array. And we'll give you back the index of that item. So this one guarantees that, well, something more complicated. It guarantees that if it gave you back an r greater than 0, then the item was at that position. It's exactly what you want it to do. If it gave you back an r less than 0, then that item was not in the array at all. And it ensures that r is greater than or equal to -1 and it's less than the length of items. Can't give you any other number other than -1 or some number that's an index of the array. Those are quite sophisticated things to be able to say. And they're written in a logical language here. So this is not the same language as Wiley uses internally for writing code. It's a logical language for writing assertions. So that's the extended static type checking in Wiley. That's super cool. And the project we want to do is do extended static type checking for animated programs, for things that aren't just maths. All the other examples of extended static type checking are dry kind of programs that take in numbers and give back numbers. We want to see what you can usefully do for animated programs. That's particularly interesting because all of the techniques for doing assured software fall down pretty quickly once you hit animated programs. That's the kind of thing that's hard for them. It's hard for them, no matter which style you're using to prove your program is correct. Whether you're using testing to prove, then animated programs make it hard. Whether you're using theorem proving to prove it, then animated, and the same here. So I think extended static type checking has got the best chance to have some useful assertions, but we want to make them and show them and that kind of thing. Yep.
Could you elaborate a little bit more on what you mean by an animated program?
Just something that draws something on the screen and changes it over time. So drawing a single thing on the screen is hard enough, but you can think of it just as a GUI program as well. Any GUI program, Firefox here is an animated program, but it's in response to my input, but we're just going more generally to animations in the draw something on a screen thing, yeah?
How do you prove an animation is correct?
Yeah, that's the question. Right, so you have to pull out what's correct is some reductionist view of it. So you can't just say it's definitely correct. But you can say, for example, that two items never occupy the same space on the screen, or the colors never go beyond these ranges, or those kind of things. Yeah. That's what we're looking to see if we can do and whether we can come up with something useful. I'm sure we can, but we just haven't yet. So on that project, last year we did generics, because we got going on this and discovered you needed generics. So a year ago, Joseph discovered we needed generics. And then 6 months ago, Elise helped us make the generics. Now we got the generics into Wiley, so we can go back to trying to work out what kind of animations we might be able to write. So as I said, this week we explore exactly what extended static type checking is. So that's a bit of a reading thing for you guys to do by yourself, and design programs that can use it. So whether we get to the point of being able to write those programs and compile them in Wiley, I'm not sure. I'll be working on the Wiley backend in the meantime, but even just designing and sketching out what that program would look like and what kind of assertions we want to put on it is good. is the aim for this week. Okay. Other questions? Nope. All right, next. All right. This one's turned into research. It wasn't research, but now it is. I've had a long-term goal to make a little, like a mini, just a piece of hardware you can plug into a TV and we can show off what our students do. And in 115, they're writing games, and in games units, they're writing games as well. We don't focus on the Unity games. We don't have the hardware for that. But the aim of this one is to build this little Raspberry Pi thing where you can plug it in and it runs games for us. We've got a fair way on that. Well, we've got a thing. You can do it now. We've got a Raspberry Pi image where if you take the image off the website, we've got, if you go to the repository, there's instructions for the image and a download of the image. If you take the image off there and put it on an SD card, then I believe it does boot directly onto the screen that shows you different games you can play, but they're all just placeholders at the moment. We haven't put many interesting games in because we've hit the benchmark, the performance problem. We're writing code that doesn't perform very well on the Raspberry Pi. And that's because we don't know what the performance of that particular style of coding is on the Raspberry Pi. So all of the programs we've written before, well, we're a Java shop in the sense that the main spine of our programming is in Java. We do some C here and some Python there and some other languages here, but that means we want our code to compile down to Java. That's perfectly good on the Raspberry Pi. It's got a very efficient Java compiler that makes good use of the hardware. And the JavaFX library, which does graphics for Java, also hooks in as well as you might to the video processing unit on the Raspberry Pi. So that's a good candidate. But it's still very easy to write programs that slow down significantly on the hardware, because it's not super strong hardware. So we built this thing a year ago. 6 months ago, we started trying to test the benchmarking. 6 months ago, we discovered you can't benchmark it in the way we might normally. So normally what you do to benchmark it is write a program that does something demonstrable, and then you'd hook into the various parts of it to calculate exactly how long it took to do this part of it, how long did it take to do this part of it, how long did it take to do this part of it. But JavaFX is optimized so that it never gives you the chance to do that. It collects up all the operations and bundles them into this big opaque thing that it sends off to a renderer, and you can't get inside to find out how long it's taken for each step. It just does it. So we learned that last time, and so this time we want to do that black box benchmarking, which is perfectly possible. It's just a different style of benchmarking. And we began doing that. Well, I began doing that to get us started. So there's now some code in here that does a basic benchmark. This is the code, not that you'll understand it at the moment. But what the code does, I've added a thing where you can run one of our applications and run it with different sized inputs. So you can run it with a small input, like 1, and it'll show 1 ball bouncing, and then you can do it with 100, and that shows 100 balls bouncing, 1,000 balls bouncing, and measure the time that each one takes. So that's how we do black box benchmarking, but we can't just make one program and run it and go, oh, that's how long it takes, because it'll be different for drawing different things. It'll be different for putting images on the screen. It'll be different for doing the physics calculations. It'll be different for drawing circles or rectangles. It'll be different once you're anti-alias. It'll be different when you've got different resolutions. Don't know how sensitive it is to different resolutions either. I suspect vary. So we need to make more of those benchmarking programs and run them and then draw the curves that go with them. And the curves will look like, because of the way JavaFX does, it holds a frame rate, and then as soon as it can't, it gives up and goes slower. So the curves are flat and then start to go slow. And that point where they start going slow is the point where you can no longer do the calculation inside that. It's inside the frame rate. Now on the Raspberry Pi, it's stuck at 30 frames a second. It won't ever try and go faster than that. It's fine. So we've set it up so that on the desktop hardware, it does the same thing. It locks at 30 frames a second. So we need to run a bunch of benchmarks and then graph out the results to see where it kicks up every time. Kicks up on desktop, kicks up on the Pi 3, kicks up on the Pi 0. And that will be that's a benchmark of what the Raspberry Pi is capable of on JavaFX. which doesn't exist yet. So not only will we do that for our own benefit so that we know what kind of programs we can write on it, whether we should be drawing shapes with vector images or we should be doing them with sprites, what kind of maths we can handle in the back end on each frame. Not only will that good for us, but we'll write up a document describing it as well for everyone else. And we'll stick it up on the archive probably because that's the easiest place to do those kinds of things. And that's the aim for this week, is to go and do all that benchmarking. There's a fair bit of Java code there to get your head around as well. So there's quite a lot of just sitting and getting into that Java code. But once you do, I don't think it's too hard to build the new benchmarks. It's all conceptual, building the benchmarks the right way. And then graphing them and writing up what you've learned about the graphs. So you can see I tried to make another one where I wanted to start. I did the one. So there's a benchmark there for drawing circles, which is I think with aliasing, anti-aliasing on at a high resolution. So that's what this guy does. And then I tried to make one. I don't think I got it finished yet, but I tried to make one for images as opposed to drawing something pixel by pixel, vector style, just sticking an image straight up. I think I got really similar results, but I'm not 100% sure on that one. So that the first step is to get the NyanCat example running and seeing if I'm really doing it right and what the performance is. Okay, so that became research. Before it was just something fun to do with Java, but now we've got to actually research the performance of JavaFX on a Raspberry Pi. As a part of it, though, you will also have to look around to see what anyone else says about JavaFX on a Raspberry Pi directly to the frame buffer. But as you can imagine, not a lot of people talk about that. Okay. Next, putting patterns through their paces. Brand new, this one. So pattern matching in functional languages is something that I'm constantly obsessed with. As I say here, it went out of fashion, came back into fashion, so now we're going to do some work on it. It's hard to explain without showing you examples of functional programming, which none of you have done yet. So this particular project, I'm just going to kind of put it out there with this description and let you decide if you're interested in it. If you've got any like sysadmin skills, you can get Linux boxes up and running and that kind of thing. That's extremely useful here because half the job here is this is really fine-grained benchmarking. We've really got to get the timing right on this. And so there's a lot of installing of the right tools on very carefully constructed virtual machines to get this working. So if that's at all interesting, that's a very good project, even if you've never seen functional programming. If you're at all interested in functional programming, then get into it. You have to learn a little bit before you can do it. But we're writing these functional programs that are a very different style to what you're used to. They rely heavily on something called pattern matching, which is nothing like pattern matching you've seen before. It's not like regular expression pattern matching. It's not like pattern matching that machine learners do. It's the older type of pattern matching, what that word meant before it got new meanings. Functional programming relies heavily on pattern matching to drive the computation, in the same way that a imperative code might rely heavily on variables. And so the efficiency of pattern matching is really, really important, but also the expressivity of pattern matching is important. And in the 70s and 80s, they did lots of research on the efficiency of it. And then in the 80s and 90s, they did lots of research to expand the expressivity of it. But no one ever went back and did the research on the efficiency of those new expressive versions. And that's what we're doing here. So I've done a quick analysis already of pattern synonyms versus views, which are two of the ways of doing it. And that came out interesting. The main thing we want to do long term is include the Edgerson pattern matching, which is a new thing that someone from Japan's been doing, and benchmark that. We know it's going to benchmark badly because the implementation is bad, but we also think long term that there's a more efficient implementation of that. So we want to benchmark the current version against the existing fancy pattern matches. Then we want to, after we've got that benchmarking done, which is probably all we get done this week, but the long term on that project is to go back and reconsider the way the pattern matching is being compiled in that system to make it more efficient and show off how efficient it is by showing that it beats the view patterns down here, which are the current winners on the blue benchmark thing. By the way, these are the kind of graphs that you'll be creating if you're doing either of the benchmarking projects, the Haskell one or the Classic Mini one. Okay. Any questions on that one? No? All right. Now I'm going to quickly bring up Irene's email in a way that doesn't expose my emails, hopefully. Nope. Oh, you can only see the side.
There, but at the bottom.
Oh, you can see it. But you're not supposed to be able to see it.
Yeah, but I can see it there.
Oh, there, but not on the string. Okay,
Yes.
cool. There we go. Ah, that's no good. Download the whole thing. Show me it. We got to shrink it just so that it
Yeah,
fits on the.
fits in the corner. That's okay.
All right. So Irene's going to talk about this. This is what Irene wants to get done. Now, we've done this a few times with Irene. It's worked really well. We got lots out of this project. So it's not strictly a computing project. It's strictly cognitive science, but we need programmers to make the project for us. Right.
Should I go and talk into the microphone?
Yeah, just hang out here on top. We'll see if
Cool, cool. All right. It's really weird because I can't actually see the people behind the screen. So for my PhD, I look at cognition of coding. So generally at how people, like which skills are involved in learning computer programming. And more specifically, what this is getting more into is how learning and using programming languages might or might not relate to using like natural languages like English or French, you know. So the next experiment that I will be running in my PhD is an ERP experiment, and I'll explain in what that is in a moment. And it's in the really early stages right now of just setting up that experiment, designing it, and we'll also have to code it so that we can then run it with participants. So the general question is, it will be looking at brain responses in response to reading errors in code, so wrong snippets of code. So EEG, I think some people might be familiar with it, is the method where you stick electrodes onto someone's scalp, and with that you can record the voltage of the activity in their brain. It's not very specific in from what area it's recording, but it's very time sensitive. So you can pretty much immediately see a response to what something that someone saw or heard in that moment. So essentially we usually put like a big cap on the participant's head with all these different electrodes, and then the data that you get looks somewhat like this. So really just one line of voltage measurements per electrode that is on the head, and then from that you would measure several participants and average across that to see if in certain electrodes you can see certain general effects in response to something that they saw. Does that make sense so far? Yeah. So this is a typical experiment that they do in natural languages and is a really well-studied effect. It's called the P600 ERP, so event-related potential effect. And this is what happens when you show people a sentence that has a grammatical error in it. So underneath the graph, you see two sentences. So the solid line is the brain response in response to the first sentence, which is the cat will eat, blah, blah, blah. And the dotted line is the response to the second sentence, which would be the cat will eating, which is clearly a mistake, right? Because that is grammatically incorrect way to say something. So you can see that the lines differ here, where the dotted line shows a big deflection, and so this is a positive voltage deflection. For some reason they plot it always with the negative up and the positive down, slightly confusing, but yeah, so a big positive deflection from the normal response. So essentially what this means is that when people read or listen to normal languages and there is a grammatical error in it, you can see that very clearly and immediately in the brain response that someone has noticed this error, a sort of like a response from the brain. And this is a really well-studied effect. that has been replicated in many normal languages, but they have no one has ever looked at whether this happens when someone would read, well, what we think might be an equivalent of a grammatical error or a mistake in a line of code. So that's the experiment that I'm setting up at the moment. So the question is, do we see a similar P600 effect when proficient programmers read code with a mistake in it? So for this, we have to set up an experiment where instead of these English sentences that you just saw, we will have really short bits of code. Some will be correct because we need to compare, of course, the two lines, and some will have a mistake in it. And so we chose to do this with Java code because it's a language that probably a lot of proficient programmers will know, and also because it's fairly restricted in what it allows, so it's easier to make mistakes in it than in some more flexible languages that people will recognize. And that experiment I will run next semester in the Netherlands, so I'm going there for the next part of my PhD, and we'll be running it there with participants, but we're already starting to design it here now. So that's what we'll be looking at doing this week. So there's two parts that I really want to focus on this week that also require programming expertise. So the first thing is to come up with these stimuli, so these snippets of Java code with and without errors, and we have to make it so that it is really one type of error that we repeat in different types of code, and that they are obvious errors that someone could spot very quickly, so that we can see that brain response very clearly if that response happens. And the second thing that we have to do is design this experiment with the software that they will be using in the Netherlands. So the specific software that they use there is ePrime2. So that's what we will have to use this week as well to code the experiment to run it there. And I'm hoping that at the end of the week we have some code that can run, and that we can then test it with an actual portable EEG headset from the cognitive science department to see what we can find. We might not really be able to get clear results, but at least we'll see whether the code is compatible and sort of works with the EEG headset, and it'll be cool to do. So yeah, I suppose the main things that you would learn from doing this project this week is just details about what an ERP experiment is, how to design one properly, how to set it up. You will learn to use the ePrime software to design the experiment with it. And we will see how to use an emotive portable EEG headset to run an experiment like this. So I think those are the main details, and people who choose to do the project will talk more specifically about exactly what the experiment has to look like. Any questions? No? Cool. Then I think that's the
The
details.
boys upstairs are going to help us get logged into these computers. I've just got to send them an email with your details. So now we just need to take, while I do that, you guys just take a few minutes to think about what you're most interested in, and then I'll get you guys to separate into groups. There's one person we didn't meet though. Who are you? Caitlin? First year BIT? Yep, cool.